Today we will talk about SPC chart example B, very similar to example A with some subtle differences, especially in terms of interpretation. So looking at lamp heights, it can be between 15 and 16 inches. Those are engineering specifications, what the engineering people say, not what our equipment can or cannot hold. It's just what they dictate. And again, today we're rounding to the first decimal place instead of the second or third. So if you have a number like that, then you just round it off to that level. Okay. And we'll calculate the X bar like we did in the first example. You add up, n equals 3 here, by the way, 1, 2, 3 samples. You add up these three numbers and divide by 3. Add up these three numbers, divide by 3. Add up these three numbers, divide by 3, etc. all the way down to get your X bar, which is another name for average. To get the range, all we're really going to do is take the biggest number and subtract it from the and subtract the smallest number from it. So you do these two numbers. All right, let's jump over to the examples. Again, I encourage you to work these out by yourself first before you jump and look at the answers. Again, you may think you understand something by looking at the answers when you may not if you actually worked out the problem first. Just a thought. All right. If you see here, the average is about 15.3. We're keeping it to one decimal place, so it's 15.3. It really would have been something like 15.33 or some number like that. But okay, and then the range, 15.4 minus 15.3 is 0.1. Biggest number, subtract the smallest number. And as I mentioned in the first video, this number means nothing. It's just a random number generator that I use to create these numbers over here. So we go through the process of the range, biggest number, smallest number, biggest number minus smallest number, all the way down to the end. And we come up with these numbers. Our X bar is the average of your X bars, so the average, and an X bar is an average of the averages. So with the average of these numbers, you add these numbers up, divide by 8, I think in this case, and you end up with 15.4. You add up the ranges and divide by 8, and you'll come up with the average R value, the range value. R bar would be the average of the ranges. And remember that we have 1, 2, 3 samples each time period. Notice this is days, not hours. The time interval could be whatever makes sense for you, and also the difficulty in getting the measurements is often a factor as well. So I use n equals 3 because again, 3 measurements this hour, 3 measurements this day, 3 measurements this day. And I use A2 of 1.023. Again, here's 1.0323 for n equals 3. D3 is 0. D4 is 2.574. Per the calculation formulas in chapter 9, we X bar we calculated. It's right there. R bar right there. And the lower control limit for X bar is going to be X bar, this number, minus A2 times R bar. So if you do that, you'll come up with this one. For the upper control limit is going to be X bar plus A2 times R bar. And you'll come up with that number hopefully. For the lower control limit for the range chart, it's going to, we have n equals 3. D3 is ended up being 0, so it's going to be 0 times R bar, which is 0. This one will be D4, 2.574 times 0.2, and that will be your upper control limit for R. So we've got these all numbers, and so again the green things are just my way to create a graph, and so you will not need to create the things in green. But if I plot the X bar chart, it will look like this. Here's the upper control limit for X bar. The X bar is orange. The lower control limit for X bar is right there. And of course this is our averages over time. So average for the first day, average for the second day, and really when I say that I'm talking about these numbers right here, 15.3, 15.3, 15.1, and you'll see how it kind of, now I don't know why it's different here. I think it's because it's still keeping some of the numbers, like it might be 15.33, this one might be 15.34 or 31, or I don't know. So actually this is just 15.3, so that's why it's a little bit off, because it keeps it's keeping the numbers that are past this, like, you know, this is 15.33, this is 15 whatever, this is 15.33, this is 15.30, and so you'll see it to be a little bit different, but that's okay. Your graph should look somewhat like this. Again, your scale might be a little bit different. I encourage you to use this graph paper tab and change these numbers like you did in example 1, make it fit the X bar chart and the R chart. If you don't want to do that and you have graph paper, then by all means use that graph paper. On the exam, I will reiterate that I will give you a piece of graph paper with the scale on it that I want you to use for the exam. Oops. So I plot the graph, and as you look at here, you say, oh, we have a problem on 9.3 with something below the lower control limit on our X bar or our average chart. We have a problem there. Something's out of control there. Something's out of control here on the top side, and something is out of control here on the bottom side again. So the process is not very predictable. And for the R chart, lower control limit R bar, and the upper control limit for R is right here, and everything is okay except for this one point, which is 9.4. Now notice 9.3, 9.5, 9.7, there are problems, but for the variability chart it's 9.4. So sometimes these line up, the numbers out of control on the top part line up with the bottom part, but not necessarily required. And here's the interpretations. For the X bar chart, the X bar chart is not in control because some of the averages exceed both the upper control limit and lower control limit. Do not put upper specification limits and lower specification limits. That's not what this question is asking. This refers to what our machine is capable of, not what the engineers say we must be producing parts to. So it's not in control, and I say specifically the 9.5 average exceeds the upper control limit. So on our X bar chart, the 9.5 average exceeds the upper control limit, while the 9.3 and 9.7 averages exceed the lower control limit. 9.3, 9.7 exceed this lower control limit. So those three are all problems. That indicates the process is out of control. And you need to have this language in about 99.73%. And that is specifically, we are 99.73% sure that something has shifted our process average both up and down in this case. We should investigate to determine the root cause of the problem. When it's out of control, when it exceeds any control limit, we need to determine the root cause, and you need to make sure you include that in your comments. The R chart is not in control because of this point, 9.4. Exceeds because the 9.4 range value 0.8, and you say where's 0.8, and there it is, 9.4. The R of 0.8, that's too much. Exceeds the upper control limit. We would not ever exceed the lower control limits on the R charts because it's almost always the lower control limits is 0. And we would say we are 99.73% sure that something has caused our process variation. not process average because it's an R chart, our process variation to increase. And we should investigate the root cause of the problem. So we have to look at problems with why is variability an issue here, and why is the center of our process, why is it shifting in the manners that make it unpredictable? Because we're saying if it below here we're 99.73% sure something has changed, we should investigate. If it's above here we're 99.73% sure, blah blah blah. And it says, is the process currently producing parts that do not meet specification? Justify. No, none of the individual measurements exceed the upper spec limit, what the engineers people say, or lower spec limit specified by the engineering department. In other words, no measurements are below 15 inches or above 16 inches. And that just simply comes back to looking at the individual readings or measurements. And we look at these and say none of these numbers are less than 15, none of these numbers are greater than 16. And that's how we would interpret that piece of it.